Good morning, good afternoon, good evening. This is your Professor Atiefreed Muhammad. This is the third lecture in the PhD Artificial Intelligence 830 at University of the Cumberlands at Kentucky. Sequential decision making under certainty. And there's a deliberate thing, a mind came on top of making. So we'll be discussing the foundational frameworks for optimal decision making in environments where actions have delayed, uncertain consequences can occur. In the rapidly evolving world of artificial intelligence, agents are increasingly deployed in environments where decisions made today have consequences that ripple into the future. Understanding how to design these systems require more than just knowing which actions produce immediate rewards. It demands a rigorous framework for reasoning about long-term outcomes under conditions of uncertainty. This lecture introduces the mathematical and conceptual tools necessary to tackle this challenge, building on the intelligent agent model and preparing the foundation for all advanced decision-making algorithms in machine learning. The learning objectives for this lecture reflect the interconnected nature of modern artificial intelligence system design. You will move beyond the intuitive understanding of intelligent agents and begin to see how their decision making can be formally modeled using mathematical structures. By end of this session, you should be able to articulate what makes an agent behave rationally, explain how environments shape the feasibility of different solutions and approaches, and understand why some methods work well in one setting but fail in another. The pharmaceutical industry uses MDP frameworks to optimize clinical trial protocols when deciding whether to continue testing a new drug or abandon it. When deciding whether to continue testing a new drug or abandon it is by itself a whole phenomena. Researchers must balance the value of additional information exploration against the cost of ongoing trials, that is, exploitation. A large pharmaceutical company models this as an MDP where states represent levels of confidence in the drug's efficiency. Actions are continuing testing or stop, and rewards are based on both lives saved by successful drug and costs of failed trials. The world rarely presents itself with perfect information. When a self-driving car approaches an intersection, it cannot see the interior of parked vehicles that might contain pedestrians. When a manufacturing robot must decide which task to prioritize, it cannot predict with certainty how long each task will take. When a hospital administrator allocates limited ICU beds during a pandemic, they cannot know which patients will recover fastest. In all these scenarios, agents must make decisions despite not knowing all the relevant facts. They must act under uncertainty. This uncertainty creates a distinctive set of challenges that go beyond what a simple rule-based system can handle. First, the agent's choice today affect what information it can observe tomorrow, creating a strategic element to decision making. Sometimes it is worth taking an action that gives a worse immediate reward because it gathers valuable information. Second, the consequences of actions are often probabilistic rather than deterministic, meaning the agent must reason about probability distribution and expected values rather than single predicted outcomes. Third, the sheer complexity of real environments means that no agent can afford to consider all possible futures. It must use heuristics and approximations to manage computational costs. Formalize the problem as a Markov decision process and solve for optimal policies. At the heart of every MDP lies a deceptively simple but profoundly powerful assumption. The future depends only on where you are now, not on how you got there. Formally, this is called the Markov property or memorylessness. Imagine you're playing chess. The Markov property means that your ability to win from any given board position depends only on that position itself, not on the sequence of moves that led to it. Two very different game histories might have arrived at identical board states, and your future prospects would be identical regardless of which history unfolded. This simplification is not always true in real world, but when it holds, it enables efficient computation. A Markov decision process is defined by exactly 5 components, each of which must be specified to fully determine the problem. The state space S is the set of all possible configurations the world can be in. For a robot, this might include its position, orientation, and the positions of obstacles. For a logistics system, it might include current package queues, truck locations, and time of day. The action space A is the set of choices available to the agent at each state. The transition model that is given, it gives the probability that taking action A in the state S will result in a transition to state S apostrophe or S prime. The reward function specifies the immediate numerical feedback the agent receives when making this transition. Finally, the discount factor gamma, a number between 0 and 1, determines how much the agent values future rewards relative to immediate ones. The 5 components of an MDP do not exist in isolation. They interact in a continuous feedback loop that forms the basis of agent environment interaction. At each time step, the agent observes its current state, selects an action according to some policy, the environment transitions to a new state according to the transition probabilities, the agent receives a reward, and the cycle repeats. This loop is not a one-time occurrence but an ongoing process that can continue indefinitely or until reaching a terminal state. Understanding the cycle intuitively is as important as understanding the formal mathematics. It helps you grasp why an MDP-based controller behaves the way it does. Each component in the cycle plays a specific role. The state encodes all relevant information about the world at the current moment. The action represents the agent's attempt to influence the world. The reward provides immediate feedback about whether the action was good or bad. The new state determines what the agent can observe and act upon next. By closing this loop repeatedly, the agent accumulates experience and, if the solution method is correct, learns to optimizes toward better and better policies. The beauty of the MDP framework is that this loop is independent of what the state's actions and reward actually represent. They could be physical quantities for a robot, account balances for the financial system, or game board configurations for an AI playing chess. So, the US Environmental Protection Agency, EPA, uses cost benefit analysis rooted in MDP principles to evaluate long term environmental regulations. When deciding on emission standards for a pollutant, Regulators must compare immediate economic costs, industry compliance expenses measured in billions of dollars today against future health benefits, reduced concerns and respiratory disease measured in lives saved over time or coming decades. The EPA formally discounts future benefits using discount rate typically around 3 to 7% annually or equivalent to gamma 0.93 to 0.97 in MDP terms. This seemingly technical choice, what value to place on life saved in 2050 versus 2024, has enormous practical consequences. A 3% discount rate treats future lives as nearly as valuable as present lives, leading to strict emission standards. A 7% rate treats future benefits as much less important, leading to more lenient standards. The EPA's choice to use a discount rate in the lower range reflects a policy value that environmental harm deserves serious weight even when it occurs decades in the future. This framework has underpinned regulations that phase out ozone depleting chemicals, successfully preventing a predicted 2 million skin cancer deaths per year by 2070, and limit greenhouse gas emissions, demonstrating how the abstract concept of discount factors translates into concrete policy affecting billions of people. Google's advertising system uses value functions to optimize ad placement in real time. When a user performs a search, Google's system must decide which ads to display and in which positions. The state includes the user's search query, their browsing history, their location, time of day, and set of available ads. The value function V of S estimates the expected long-term revenue Google will earn from this user interaction, not just the immediate click through, but also the user's future engagement with the platform. So future searches that show ads, subscription likelihood, and so on. By computing the value functions for different ad placements, Google's system learned that showing a highly relevant ad to a user likely to click it increases V of S, while showing irrelevant ads might decrease the V of S through user dissatisfaction. DeepMind's AlphaGo Zero system learned to play the game of Go at superhuman level using a sophisticated variant of Q-learning combined with neural networks. The game of Go has an astronomical state space more possible board configurations than atoms in the universe. So storing explicit Q values is impossible. Instead, AlphaGo Zero used a neural network to approximate Q values. Starting from random play, the system played against itself millions of times. After each game, it updated the network's Q value estimates using observed rewards and the Bellman equation. Each position in a game became a training example. In this position, the move we selected led eventually to victory. So Q value of the move should be high. Over months of self-play, AlphaGo Zero discovered that certain Q value consistently predicted winning and losing positions. It learned to favor moves with high Q values, eventually achieving superhuman performance. Industrial example I would like to share in the optimal policies would give you an exact understanding how deterministic, stochastic, and optimal utilization happens of the artificial intelligence. The Boston Dynamics, which creates advanced humanoid robots like Atlas, and bipedal robots like Spot uses MDP based optimal policy computation to control complex locomotion. Walking quadruped, this is a good word, quadrupedally or bipedally on rough terrain with unknown footholds. In an enormously complex control problem, Boston Dynamics engineers model the robot's current state as a vector of joint angles, joint velocities, body height, and terrain slope estimates. The actions are target commands to each joint motor. The reward function encodes the goal, move forward at a desired speed while maintaining balance and minimizing energy consumption. By solving for an optimal policy using algorithms related to value and policy iteration, Boston Dynamics control systems compute the exact torques to apply to each joint given the current state. The resulting controllers are so good that Spot robots can navigate unstructured outdoor terrain, climb stairs, and even recover from being kicked. The ability to compute and implement optimal policies under real world constraints, noisy sensors, imperfect knowledge, computational limitations has made Boston Dynamics robots industry leader in mobility. Their latest robots are already deployed in industrial inspection, disaster response, and research environments, validating that the theoretical framework of optimal policies translates into practical robotic capabilities. So, Intel and other semiconductor companies use value iteration to optimize manufacturing processes in chip fabrication plants. Model, or rather, modern semiconductor fabrication facilities, fabs, are among the most complex manufacturing environments in existence, with hundreds of processing steps, thousands of machines, and produces the products moving through the facility per weeks. Decisions must be made continuously. Which product should be a machine processed next? Given that different products have different priorities, different processing requirements, and different profitability, fab managers model the system state as the current queue of products waiting at each machine, current machine availability, and current profit margins for each product. Using value iteration, they compute optimal dispatching policies, rules for which product each machine should process next to maximize long term fab throughput and profit. So the resulting policies are complex. They account for interactions between machines, future demand forecasts, and equipment reliability. But value iteration computes them offline before the fab operates. During live operation, machines simply follow the pre-computed policies. This approach has helped Intel and other fabs reduce cycle time, the time from raw wafer to finished chip, by 15 to 20%, while increasing throughput per machine, translating into hundreds of millions of dollars in recovered productivity annually. So the advantages are simple to implement, guaranteed convergence and find optimal values, and the disadvantages of value iteration computing V star of S are requires full model, slow convergence, may do many iterations, used when environment model P given P of S a prime given S and A is known exactly. DeepMind's Atari playing agent DQN or DeepQ network was built entirely around iterating on the Bellman equation for Q values. The agent learned to play dozens of Atari games at superhuman level by repeatedly applying the Q-learning variant of the Bellman equation. So the DQN success, playing Space Invaders, Pong, and Breakout better than any human ever had, showed that 30 years old Bellman equation combined with modern neural networks could still solve problems in entirely new domains, validating the timelessness of this mathematical insight. So the convergence is policy iteration converges in fewer iterations than value iteration. Through each iteration is more expensive, requires policy evaluation. So when to use the value iteration is large state space, quick approximation needed. Policy iteration is fewer improvements desired, can afford evaluation cost. So you can see that the complete mathematics is given here for you to follow and convert this into a mathematical algorithm coming from the metadata of your state space, and then in the end of the day you can write Python program on top of it. Tesla's autonomous driving system exemplifies the journey from dynamic programming, simulation-based, to reinforcement learning that is experience-based. Initially, Tesla engineers used dynamic programming-like approaches. They built detailed simulators of driving scenarios, computed optimal driving policies, assuming perfect knowledge of vehicle dynamics and sensor characteristics, and deployed these policies on vehicles. This worked well for structured scenarios like highway driving. However, as Tesla expanded to complex urban driving, they found that accurate models were impossible to build. Pedestrians' behavior is too variable, the occlusions too common, edge cases too rare to simulate realistically. Tesla then shifted toward reinforcement learning approaches, collecting real-world data from millions of vehicles, learning from actual accidents and near misses, and using this experience to refine driving policies. The result is a system that combines both core dynamic models for physics using DP, learned models for pedestrian and driver behavior using reinforcement learning, and continual refinement through new experience. This hybrid approach has allowed Tesla to handle unprecedented complexity, safely deploying autonomous systems that encounter millions of novel situations daily while continuously learning and improving. The concepts covered in this lecture, MDPs, value functions, optimal values, are not academic abstractions but practical tools deployed in systems affecting billions of people daily. From recommender systems that decide what to show you, to manufacturing robots that decides what to build next, to financial trading systems that decide what to trade, the MDP frameworks provide a principled way to design agents that act optimally in complex, uncertain environments. The reason these applications succeed is that the MDP framework, despite its mathematical sophistication, captures something essential about decision making. You must balance immediate and future rewards. You must act despite uncertainty, and you can improve by learning from experience. So the power grid operations example that I would like to share with you is a combined with broader grid management, shows how an entire class of critical infrastructure systems increasingly relies on MDP based decision making. Grid operators must balance supply and demand second by second, deciding when to stop generators, which lines to activate, and when to shed load if necessary. Modern grids are making this problem harder by adding variable renewables, solar and wind, with uncertain output, adding distributed generation and storage, and increasing electrification, electric vehicles, and heat pumps, creating new sources of demand rather than relying on rule based approaches like start generator X when demand exceeds 80% of capacity. Grid operators are deploying MDP based systems that optimize for system stability, cost minimization, and renewable integration simultaneously. So, the industrial applications and key takeaways for this lecture is robotics, game playing, resource allocation, and network control. So the Markov property enables tractable computation of optimal policies. Bellman equations recursively decomposes long-term value into immediate and future reward. So the concepts covered in this lecture, the MDPs, value functions, optimal policies, are not academic abstractions as I had mentioned earlier. So I strongly suggest you to look at the material that is available in the introduction to artificial intelligence by these two great authors that have been among us, and one is serving Google, the other is actually working at the moment in the UK, and Stuart Russell and Peter Norvig. I started learning my artificial intelligence in 1995 from the same book that we are discussing in this PhD AI 830 for our pragmatic understanding, because the latest version of the book does contain all the brand new advancements that happen in the artificial intelligence domain. See you in the next lecture. Stay healthy. Professor Atif out.